So I see everyone got a seat, more or less. Very well. Very happy to see so many of you here today. I will take this in English today. I would like to welcome GEO Wednesday to the Science Library. GEO events are really dear to my heart, and I'm really happy to be here today and open the first GEO Wednesday here at the library. This is our first meet, but we will see each other every third Wednesday of the month. And this is basically that the Department of Geosciences would like to have a monthly arena here at the library for us geo people to meet, and researchers and students, but also these presentations are, of course, for everyone who's interested in the geosciences. And now I would like to give the word to Bjørn Jamtveit, who's a professor in geology.
Thank you. So it's my pleasure today to introduce Olivier Galland and his exploration of volcanic roots. Olivier is a researcher at the Department of Geosciences and belongs to a section called the PGP, or Physics of Geological Processes, that used to be a center of excellence starting in 2003. Now, Olivier is, as you will hear very soon, French, where he studied at something called École Normale Supérieure. It's one of these French normal and superior schools. It's very hard to get in. And after that, he did his PhD in Rennes. And what he was studying was the emplacement of magma, so molten rocks, below the surface of the Earth. Not at the top like volcanoes, but into the rocks close to the surface of the Earth. And he was studying how this emplacement process was coupled to mechanical stresses in the Earth crust, where the magma was emplaced. And these stresses were then caused by plate tectonics by the South American continent colliding with the Pacific plate, or whatever these plates were called. So this is an issue that he's still very interested in, how molten rocks are getting into the Earth crust and how this is coupled to other large-scale processes where continents and the ocean floor is moving around. Olivier has been with us at PGP from 2005, so that's 12 years already. In 2008 to 2009, he did a very famous long biking trip from the southernmost tip in South America, and for 9 months they were biking, Caroline, his wife, and Olivier, up to Peru. In the end, I think even their bikes were stolen. Yes. So it was an even longer trip than they expected. So he has lots of experiences from South America, both from his PhD and from later bike trips, but also field trips. He's arranging a number of field trips and has been there several times visiting the volcanoes in Argentina in particular, close to the Andes, a place called the Neuquén Basin. So today he will tell us something about volcanic roots. I expect that there will be presentations of his field experiences, but he's also conducting quite a number of experiments where he studies the emplacement of melts in a solid or semi-solid environment. And so this part of what he's doing today is also connected to one of these strategic research initiatives, or endringsmiljøer, we call it in Norwegian, which is called Earth Flows, and arranged as a collaboration between various sections at the Department of Geosciences, people from the Department of Physics, and also here from the Department of Mathematics. So we look forward to your presentation today, Olivier.
Thank you, Bjørn, for the very nice introduction. I really also would like to thank the staff of the library for organizing this GEO-onsdag, GEO Wednesdays, and especially Edina and Merete. So because, as Edina said, it's the first GEO Wednesday event, it was not clear about the format, the audience, etc. So the instruction for the content of the presentation was not really clear. I had one clear instruction: it must be very good. So I have no pressure. But fortunately, I will talk about the topic which is usually quite fascinating. I don't need to speak much, but just to show what happens is always, sufficient to be caught and to be really hypnotized by what's happening. I will talk about volcanoes, but especially volcanoes' roots, and I will try to guide you through a journey to Patagonia and Blinderns basement, and you will see why. I will stop talking for a couple of seconds, and I will just show you what I mean by it's beautiful. So these are images of the Patagonia eruption in 2014 in Iceland. Well, I just took it from YouTube, so it's a DJI for the drone. It's an advertisement for the drone. But then when you look at that, it's absolutely beautiful. It's fascinating. It is really what fascinated me when I was a kid. And since I was a kid, I wanted to be a volcanologist. Here I am. I think I'm extremely lucky. But it's true that when you look at that, it's really, really nice. It's beautiful. Of course, there are some key challenges to access volcanoes. The lava fountains are 1200 degrees, so it's extremely hot. So you don't approach that. But when it's only like spitting like this, it's still fine. But then you have other types of eruptions. This is another Icelandic volcano, the Eyjafjallajökull volcano eruption in 2010. I'm sure you all remember that. This bloody volcano prevented me to go to Corsica for a field trip. Instead, I went to Western Norway under the snow. So I was rather pissed. But there is another challenge of accessing it. It's really explosive. It's what we call a Plinian eruption. And then you see these big blocks just ejected. Yeah, that's rather, yeah. These images are quite fake because it's really using a zoom lens. So this guy looked very, very close, but not that close, because otherwise people will be just crazy. But it's just absolutely amazing. It's really violent, it's really hot, so obviously there are many challenges to study volcanoes. And you see here, it's really spitting hard, it's really exploding, so you don't want to approach that because, of course, I mean, we want to have a long carrier, not a short carrier, so we want to actually not approach these monsters too close. And there are other challenges, is that what we see at the surface is just the eruption, so the magma is coming out of through the Earth's surface. The only problem is that this is the end result of a long process. So the magma is generated deep into the Earth, and then the molten rocks migrate through the Earth. It can migrate vertically, but it can also migrate horizontally. It can stall for some time. It can accumulate in big blobs like this, evolve, change chemistry, change physical processes, etc. And this is the combination of all these processes at the roots of volcano, what we call the volcanic plumbing system, that lead at the end to the eruption. So all these processes at depth control the dynamics of the volcanic eruptions. So if we want to understand eruptions, if we want to predict, for example, also their character, their energy, etc., we need to understand what happens at the roots of the volcanoes. But of course, there are also many challenges. It's possible to switch off the lights. I don't know. I think it would be better image, better colors. Yes? Okay, thank you very much. So this is a satellite image of a very active volcano. Oh, thank you. That's great. It's Piton-la-Fournaise, a French island in the middle of the Indian Ocean. And then here we see, for example, all the black things which are fresh, and also like gray things which are fresh lava flows. So the thing is that, okay, this is the summit crater, and you have eruptions all over the place. But overall, we see clearly that everything is covered by lava. So how can we know what happens below? It's very, very difficult. We can use geophysical surveys, for example, but still, we don't have direct access to the root, to the core of the volcano. So if we want to understand where eruptions will occur, it could be here, it could be here. There's actually even like an eruptive vent here, here, there. We need to really know what happens at depth, under the surface. So this is a topographic map of the whole Réunion Islands, and this we see the active part of it, so the Piton-la-Fournaise volcano. But actually, this is only parts of the island. The rest of the island is actually made of a bigger, older volcano called Piton-des-Neiges. And what we see, so the summit is in the center here, what we see is that the Piton-des-Neiges volcano has been dissected by deep valleys. So which means that erosion excavated the flanks of the volcano and now is exposing the subsurface, the core, the roots of the volcano. So there could be a nice possibility to study what happens below the volcanoes, also what's feeding the eruptions. But again, we have challenges. So this is a picture, sorry, of this valley. It's called the Sillaos Valley. So there are several challenges. First of all, the access. You have like 1 kilometer high cliffs, almost vertical cliffs. That's difficult. You can have also a lot of vegetal cover, forests, especially in these tropical islands, which even make it even more difficult. But actually what is really more challenging is that all the rocks of the lava flows, but also of the volcanic roots, are made of the same rock type. So for example, the rocks of the roots are made of basalts, which are black rocks, and all the lava flows are also basalts, black rocks. Black rocks versus black rocks, it becomes extremely difficult to really see what is a conduit in a volcano from what is the surrounding rock. So clearly we have a big challenge to really understand and map the structure of the roots of volcanoes in these islands. So ideally, what we need to do, or to look for, are places where we have actually volcanic conduits, but in rocks of completely different rock types, so that we can really see and study in detail the structures of this. And fortunately, there are several places on Earth, like for example in eastern Greenland, where the magma has been placed into sedimentary rock. So this is a very spectacular field helicopter photograph, so provided by Christian Heide at the University of Bergen, where we see a tongue of magma here, it's basalt, going there, intruding into layered sediments of very different colors and features. So now, while we have that, we can really study the structure of the volcanic conduit here and how actually the host rock is structured, so understanding really how the magma is propagating, intruding into the Earth's crust. So ideally, we'd like to see and study the volcanism in a geological setting of sedimentary basins. And there are many places in the world. For example, this map displays in yellow the distribution on the Earth's surface of sedimentary basins. So there are many. But also in red, it displays also locations where you had really big volcanic events, what we call large igneous province. And then we figured out that many of these big volcanic provinces overlap with sedimentary basins. So they were formed into geological setting of sedimentary basin. So that's great. So there are potentially many places to study. In detail, it's a bit more complex. But of course, now when we talk about sedimentary basins, this is also where, we always have the smell of oil, hydrocarbons. Hydrocarbons are also where formed into sedimentary basins. And now it becomes interesting that the volcanoes also have their part in the generation of hydrocarbons. And this is a nice example coming from Argentina, so the Neuquén Basin, and we'll talk about that more. It's called the Aucamahuida volcano. It has 2 million years old, so it's not very, very old. So we see here the summit crater. It's a huge volcano, it's like 50 kilometers in diameter, covered with basalts. And we can see a lot of these mounts are volcanic vents. But we also see many white dots up to the really summit. And each white dot is actually a platform with an oil well. So this is a picture. I think this is this one here. So we really have like a pumping well, pumping out the hydrocarbons at the really top of a volcano. So that has become interesting, how the volcanoes can actually control, affect, impact the generation of hydrocarbons, and this is really not clear. And this also, when you look at that, this is the structure of this volcano. So where we see, okay, we have a volcanic cover, we have lots of sediments, and in the sediments, we have these horizontal sheets or tongues of magma that intruded into the sediments and completely affected the evolution of the sediments, the evolution of the organic matter, which led subsequently to hydrocarbons and oil. But there is a big question mark, is that there are huge parts of the roots of this volcano and how the root of the volcano impact hydrocarbons, which are not known. So clearly, we have to understand better how the subsurface processes of the roots of the volcanoes form, to first understand volcanic processes, and second, to understand also how this volcanism can control or affect hydrocarbon systems in sedimentary basins. So this is the only slide with text, to be sure. Yeah. So, but just like a list of what we're studying of the impact, the implications of volcanism on hydrocarbons. So first of all, it triggers maturations. So magmas are very hot, and when they intrude into the sediments, they heat up the sediments, crack the organic matter, actually generate hydrocarbons. They can also, the volcanic conduits can be also aquifer and hydrocarbons. And for example, in Argentina, the oil companies pump directly from the volcanic conduits, and this is really unconventional. It can produce structures in the overburden. We can actually trigger some traps. It can produce damage, fractures, etc., which really affects how the fluids can flow around the magmatic conduits. So fluids mean water or hydrocarbons. And then there are other issues. But we in Oslo, we have a group with many very nice, smiley PhD students working on different aspects. And that's it for now. But let's come back to what is more interesting. So especially during the last, 2 decades, not good, I've been focusing on working on this basin here, called the Neuquén Basin. And you will actually think you will understand why I just keep going there. So let's have an overview of this basin, of this area. So it is located here in northern Patagonia, so like a few hundred kilometers south of Santiago de Chile. And you see a satellite image of part of the basin. So the basin is here, to the left of this gray line, and slightly across the Chile-Argentina border. And what we see all these red, orange, and like gray-green things here. So it's first of all, it's desertic, so that's great. There is no vegetation at all, so things are outcropping, which is very good. And we see all the rocks. And the red, orange, and gray-green here are the sediments of the basin. So we can see a lot of stuff. But also what we can see, we have these dark gray blobs here, here, and even like big one with very black, and here, there. These are big volcanoes that formed into the sedimentary basin. So you have a lot of volcanoes. So that's really cool because this seems to be a very nice place where we can study the volcanism in sedimentary basins, and especially because thanks to the Andes, the rise of the Andes, the orogeny, the mountain building, brought deep rocks to the surface that we can also study what used to be the roots of volcano, now the surface. So that's very good. Just a close-up around this volcano here, which is called the Pajun volcano. It's a big volcano, it's a Landsat image. And we really see these long lava flows. So you see the scale, it's rather big. Big ones. Big volcanic, so all the black things is a cover of lava flows. But then to the west part of it, this is part of the Andes Mountains already. And the Andean tectonics brought the sediments and the roots of volcanoes at the surface. So we can study almost the root of this big volcano here at the surface. And this is what I will show you. But so there is geology first, there is research, but going there and doing some field work there, it's a bit more than just research, it's a bit more than just science. It's also a life experience. So now I will show you like a 3-minute movie of the conditions we have in the field there. Actually, stop talking for 3 minutes.
Se fue alejando y quedé con tu partida, con los ojos empapados de llorar tu despedida.
Cuando se quiebran los sueños, como un cristal en las manos, son profundas las heridas que de amor nos van matando.
Anoche no dormí,
cuando apagué las luces vi tus ojos y fue como
luz del sol dentro de mí. Anoche no dormí, tus besos me estuvieron desvelando. Anoche fui feliz con solo los recuerdos de tu amor. Que mueran ilusiones y esperanza.
Los días enteros paso recordando nuestra historia. Las noches enteras ando con tu amor. En mi memoria. Anoche no dormí. Como sentí
toda la luz del sol dentro de mí. Anoche no dormí, tus besos me estuvieron desvelando. Anoche fui feliz con solo los recuerdos de tu amor.
Good. Very difficult to talk about after that. So yes, this is, I mean, you see that quite a few events happened during the field. So for each image, I think we had at least 10-minute story. So I will not go into these stories now because otherwise we have the whole afternoon. So, but you've seen already that, you know, it's a desert and it's very beautiful exposures. So we'll show you briefly what we see when we're on the field. And especially with the kind of types of magmatic conduits which are exposed at the surface. And when we start looking in details, we see quite a broad view of things. And Tobias, who is there, can talk about that more. But we find, pointer is here, we find very different types of magma conduits. We can find these very horizontal, so these represents the layers, the strata, sedimentary strata. And in this sedimentary strata, we can find flat sheets of magma we call sill, or they can have like saucer-shaped sills. Sometimes they can be conical like this, like a cone, or we can have also magma accumulating in the doming the overburden here and just producing a laccolith. And sometimes we have a big blob here, which bulldozers the rocks and producing like really big, almost like rounded intrusion. So for example, I will show you some examples of these horizontal sheets. And this is an outcrop we found 2 years ago. And you will see, so we see some brown cliffs, and each cliff corresponds to one of these magmatic sheets. And in between, you have the sediments, which are shared, so organic rich material, or rock. But actually, this is only part of a huge section we found. And it can continue like this forever, for kilometers. This is absolutely fantastic. We see the whole route of Volcano. The thing is like 8 kilometers long. It's 500 meters high, so it takes a while for actually studying all that. But still, this outcrop is very relevant because it's situated here. So the parts, the section I just showed you the picture, correspond to only this part here, and you see it continue to the north, and it continues to the south. But these things which are at the surface now are actually in the subsurface here. So here you have a big fault bringing the deep material to the surface. So what is outcropping there is at 1 or 2 kilometer depth, a few kilometers to the east. And what you see here, again, we see these white dots here, the same as earlier. And each white dot corresponds to a well. And there, in this area, YPF, so the National Argentinian Oil Company, they are pumping out oil and gas. And the reservoirs are actually the magmatic sheets, the magmatic sills. And the thing is that, so they don't really understand what's happening there. So each red line here corresponds to one of the oil reservoir. They only have subsurface data, wells and seismic data. But thanks to the Andean tectonics, what is at the depth here is now exposed to the surface. So at the surface, we have what we call the field analog of what is producing now currently in a few kilometers. So really this outcrop is very interesting for understanding volcanic roots, but also to understand actually how these volcanic roots can control or impact and also host the hydrocarbons. And I will not give you the results because it's a bit technical. And also mention these blobs, big blobs of magmas, which are called laccolith. And we found a few of them as well. For example, this big one, very big, it's like 1 kilometer in diameter, probably 1 kilometer thickness. And it has been eroded, so now it's at the surface. It's sticking out like this, like a cathedral. And it's quite a challenge to access sometimes. And we have other ones which we have also studied in detail. For example, we have one blob here, which sticks out, another one here, and where I was standing when I took the picture, the third one. So really study in detail the structures of these, and overall, well, here we don't see well, but the structures of the sediments which are surrounding these magmatic blobs. The reason is that also a few kilometers to the south of these blobs, they are in the subsurface, so they're not eroded, and they are also hydrocarbon reservoirs. So this is a simple drawing, a geological cross-section showing a profile, where we see several intrusions here, and we see some wells, and here the wells found oil and gas within the magmatic bodies. So it becomes very interesting to understand the structures in the magmatic bodies, but also in the surrounding here, because the way the rocks surrounding the bodies are deformed will control how these bodies are good traps or not. So it's very important for us to understand all the deformation and the processes that accommodate the emplacements of these blobs. And here it comes the emplacement mechanisms. Because what's the core of my work, and this is what Björn mentioned, is that I really want to understand how the magma are actually intruding into the Earth's crust. And for that, the magma comes from depth, wherever it is, and it's overpressured, and it wants to make its own space. So, for example, it can spread horizontally, but because there is confinement, it's pushing the rock, and the push of the magma either trigger like small-scale damage, so it can produce fractures, etc., all around, but also it can produce large-scale structures like domes above it. Just can lift up like several kilometers of rocks, and this is really the deformation of these surrounding rocks, which really accommodates how the magmas are emplacing into the crust. So it is really important to understand all of this. So having that in mind, we also found very nice outcrops where we see the intrusions, and then where we also can see the deformation of the surrounding rock. And I will also show you a movie of that. Yep. So here we have one of these magma body here, and here we see the layering of the sedimentary rock. So it's very nice exposure. We have the igneous body, the magmatic body, and we have the structure of the surrounding sediments, and we can map the structure of the sediments. So just for scale, we are here. So I was piloting a drone from there. And so you see, that's nice. Yeah. So we have two tall guys here. Trond, who's there, I saw, and me. Yes, so just for the principle, this is a picture from the drone. So we have the big body of magma here, solida, another one here, and we see nicely the layers of the sedimentary strata in the surrounding rock. And the goal of that is to first, of course, map the magmatic bodies, but also map in great details how the rocks, the surrounding rocks, are deformed to see how they accommodate the space for the magma to come. And especially what is interesting, we can see here that the strata are not deformed at all. And here, this is the same strata, which is completely folded, distorted. And this is what we really try to look in detail to understand how the rocks deform when the magma came in. Another problem is the access. So this doesn't seem that steep, but that's steep, and that's quite unstable. And it's a big one, it's a big outcrop, it's more than 1 kilometer. So just for information, at that outcrop, so my camera rolled down 20 meters because it was steep, so it survived. Amazing. And then our backpack rolled down much more than 20 meters, and it actually opened. And all the sheets, the sheet paper, actually rewrote all the notes, went into the landscape to actually run after them. We managed to get them all. It's a miracle. So just to say, it's not super easy to really map these structures, especially they're big. And because it's very steep, we basically have the face on the outcrop, and we need to have a bit more vision, broad vision. And this is where, again, the drone is very important. So with the drone, we surveyed the whole outcrop, and we took many pictures, like this. And what we do afterward, we use these pictures, and we put them in a program, a photogrammetry program. And this is what we do. Oh, this is not what I wanted. With this photogrammetry program, we use these pictures to actually compute the outcrops in 3D. So when we start zooming in, so this is the outcrop, but it's in 3D. So we can really almost like reproduce, model the outcrop in the computer so that we don't have to go in each small place, and because it is very steep, and it's more than steep, it's a cliff. So actually, we can really do, after the field work, we can come back to the lab and follow each layer and actually really do the complete mapping of 1, 2, 3 kilometer outcrop to really have a great understanding of what happened. Otherwise, we would need like 2 weeks there to do this mapping. So that's quite an improvement. And if I zoom in, for example, just to show, this is a bit, but we see a lot of details. I mean, it's much better resolution. It's much less than 1 meter, so like a few tenths of centimeter. That's the resolution out of a 1 kilometer long outcrop. That's pretty impressive. Right. But that was the journey in Patagonia. What about Blinderns basement? So it's stuck now. Never mind, it will come. But what is interesting there is that we see the things. We see the volcano's roots. The only problem is that these are old systems, are frozen, are basically static, and we see the end result of a long series of processes and phenomena. So really to understand the dynamics, the rates, and how it formed, it is extremely challenging. So that's already good, but that's not sufficient. So and really what we try to do, especially at the group PGP, we try to also really understand the physics of these processes. And sometimes we figure out that the fieldwork is not sufficient, so we try to do some modeling. And because I'm not a physicist, I like to do experiments. And we have developed in the basement of the physics building, we have developed a lab where we actually can, or we try, because we don't claim we do, but we try to reproduce the processes which happen at the roots of volcanoes. And I will show you a few experiments. So first of all, this is a photograph of what we call the cage. And this is the box. So we actually try to simulate volcanoes in these small box. And the principle is like, it's a square box of 40 by 40 centimeters, in which we put very fine powder. So it's a bit like flour, but it's minerals, like silica flour, that simulates the Earth's crust. And then we have oil, which is injected here through an inlet with a pump at constant flow rate, and the oil simulates the magma. So just the oil is just French stuff we used to actually cook French fries in France, végétaline. So anyway. So the oil is there, and it simulates the emplacement of the magma through the crust. But the advantage of this oil is that it melts at 31 degrees C, but it's solid at room temperature. So after injected, molten, it solidifies because it's never 31 degrees in the lab. So it solidifies, and then we can excavate it, and we can actually observe the structure of the solidified magmatic conduits. And also in this setup, we have 4 synchronized cameras, which are there, that we use to monitor the surface of the models, and we can see actually quantify how the model deforms when the oil is intruding. And I will show you some results. So this is an excavated magma conduit, solid. So it's almost like archaeologists. We just dig out all the flour. Be careful not to break because it's very thin. It's a couple of millimeters thick. And at the end, we have the full shape of the magmatic conduits. So that's rather fun. And we use different materials for simulating the Earth's crusts because, you know, you have hard rocks like limestones or conglomerates, but we can also have loose rocks, weak rocks like shale or unconsolidated sands. And we need to take that into account to understand the emplacement of magma into the crusts. And for that, we use different materials. We use silica flour, which is cohesive. So you see, it's stable on its own weight. So basically, it makes some blocks, some tensile cracks like this. So it's not that loose. It can actually sustain some stresses, which then these simulate like hard rocks. And the loose rocks, we used another type of powder, micro glass beads, 40 micrometers diameter. And this is like sands. It basically collapses under its own weight. There is no strength. And then we use these 2 materials to reproduce or to simulate hard and soft rocks. And I will show you only 2 experiments. What happens when we inject the magma into hard rocks and when we inject magma into soft rocks. So these are experiments like made by Tobias Schmidl. And I will show you an animation of a picture, an image of the model surface, corresponding topographic map, and the topographic scale is in millimeter. And then across the topographic map, we can follow the evolution as a profile here, and also it's in millimeter. This is what we get. So basically, we don't see anything. So just see what happens here. We see that we have a gentle dome forming while the magma is intruding into the experiments. And at the end, we have eruption here, which is highlighted here. So we have a smooth uplift, broad dome, 20 centimeter in diameter, 3 millimeter of amplitude. So that's interesting. It's what we see in nature. And also what is interesting is that when we excavate it, this is the excavated magma conduit, and it's a flat, very thin magma conduit, exactly like what we saw in the field, these seals. So this is what happened in hard rocks. What happens in weak rocks? So that's the same image, topographic map, and profile. And there we have a complete difference. So we have like almost like things bulldozering the rock, lifting up everything. You have like 1.2 centimeters, and very blocky, very angular and irregular. And at the end, we have eruption also of the oil. So completely different deformation of the model surface. And so what do we have when we excavate the magmatic body? We have a blob. It's almost like a shape of a cork. So in a way, it also represents quite well what we saw in the field. That means that these models are able to model these thin sheets, what we call seals, to these big blobs. So, and these models are the first ones who are actually able to model such diversity. And we have been running many, many experiments to really understand when this forms, and actually how the surrounding rocks are accommodating the emplacements. And we basically are the first one to be able to do that in the lab. But, okay, let's push a bit, 5 minutes more. What I've shown so far are only the deformation at the surface. But what we're interested to know is also what happens like really in the subsurface, at the vicinity of the magma when it's pushing a host rock. And with this experiment I showed, it's not possible. So we have another PhD student, Ben Rogers, who's not here, he's doing lectures, who is using another type of experiment, which is actually very, very cool. It's not 3D, it's 2D, so we have to imagine a cell here. And the cell is made of two glass plates, two parallel glass plates, and the gap is a few millimeters thick. And this cell is filled with a gel, laponite gel, which is a mixture of clay particles within water. And this gel, actually, when you wait a bit, the clay particles interact with the water, make some chains, and produce a gel, like jellies, like the English like that. And it's transparent. And in this gel, he injected red oil to simulate the magma. And also he was following what was happening during the experiments. So this is a small, short animation of that. So the gel is, and you have also diffuse light source in the background to highlight that. And when you look in detail, so the gel is transparent. And this is what you will see maybe, yeah. And you see the magma, which is propagating, intruding, and producing complex pattern, accumulating, and at some point going up and splitting, and it's doming at the surface, and then the magma is coming up, poof, it erupts. That's really cool. The only problem here is that, yeah, well, it's cool. We see the conduit, but what happens in the surrounding gel? We don't see anything, and you can really, by the eye, you don't see anything. But these gels are actually very cool. Why? Because they have very strange optical properties. And I will show you how we can take advantage of that. This is again the setup. And what I didn't talk about that, but between the light source and the cell, we have a polarizer sheet, which polarizes the light which comes from the light source. And then on the camera, we have another polarizer, but which are perpendicular. So if we just consider normal light source, these two cross polarizers should just kill all the light. And this is indeed the same experiments, and it looks completely black because it's monitored with these two cross polarizers, so there's no light coming through. But this gel, when it's deformed, is actually able to modify the light, rotate the light, such that actually when it's deformed, strained, etc., through these cross polarizers, we can see some light coming through, so that you will see that there will be some halos of light, and that will show where the gel is deforming, and that's absolutely stunning. And now we see everything, and this is the exact same experiment as I showed before, but with two cross polarizers. And then we see these cracks here, boom, 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 boom. Poof, here it is. So now, with these simple optical techniques, we really want to really quantify and understand how the gel is deforming to accommodating the emplacement of the magma. And now we try also to understand and control the mechanical properties of the gel, like the viscosity, the stiffness. And I will just show you another movie with a stiffer gel, and that's really cool as well. And we see these long cracks forming through the gel. And then suddenly you have the magma which is accumulating, pushing. You see the dome here at the surface, and then you will see a crack initiating from the surface, going down, and then the oil will continue and just going up like this, so we can really image and quantify everything of what happens in the experiments. It's absolutely beautiful, and as far as I know, it's the first experiment where we can really see what happens when surrounding the intrusions. So this is the only thing we have for these experiments. So now we have to think of how to make sense out of it, how to quantify the results, but really already seeing what's happening, it's already a fantastic breakthrough. So we'll not continue more. Just say that, okay, what I've shown is only a part of a multidisciplinary research where we integrate fieldwork in the American basin. We're also doing some seismic interpretation in volcanic basins. As you saw, we do quantitative laboratory experiments, but also we have two postdocs working on theoretical and numerical modeling, and we try to integrate everything to really bring new understanding of the roots of volcanoes forming through the brittle crust. And for just finish, just want to show this bunch of funny faces. And they are not only smiley on the pictures, but in real life, and it's a real pleasure to work with them all. And I really hope that we'll come up with very nice research results. And I really want to thank them all for their enthusiasm and also for being smart. I really appreciate that. Thank you very much.
Thank you very much, Olivier, for this very fascinating presentation of aspects of our very dynamic planet and how to go about to understand the processes behind the patterns that you observe in the field. And not the least, how challenging and sometimes even dramatic it might be to be a field geologist.
Yeah, we have many stories to tell. Yeah.
I believe there is some time for questions. Is that right? Does anyone have any questions or comments to Olivier or his Volcano group that I see several members of here?
Okay.
There is one in the back.
Hi. What are the challenges related to getting the stress field directly from the polarization measures? Is there any way to calibrate this thing to...
I'm sure there is.
Yeah? Not so easy?
I'm sure there is. We just need to come up with something. So, but I mean, there are two things. So first of all, okay, we can say we want to calculate the stresses from this birefringence halo, right? Which is challenging. But also what we can say, we can already try to quantify even, for example, this shearing fractures, these jumps in terms of in the birefringence, already quantifying the extent, the length, and the density of these cracks, we don't know. So we can already just learn a lot just by doing that before even trying to quantify the whole stress map and the whole strains map. But we have actually an idea. So because now the gel, the experiments we have with the gel, it's perfectly transparent, it's homogeneous at microscopic scale. But what we want to do, we want to actually introduce some small seeding particles, these poppy seeds, so that in addition to this stress halo or birefringence halo, we could also compute independently the displacement field and so the strain field. And so we want to see if actually the intensity of the birefringence correlates or not with the strain to see, and if it does, then locally it can be elastic stress. If it doesn't, we're beyond elasticity, and it's either viscous flow or plastic yielding. That's an idea. It might be not feasible, I don't know, but at least we need to try to see if it's possible. And if it is, that would be super cool.
Anyone else? Yes?
The volcanoes, is it a kind of a pattern? I've heard about the ring of fire. Is it?
The ring of fire, yep.
Yeah.
So, well, then we go bigger scale than the volcano. So what we call the Pacific Ring of Fire is basically an almost continuous range of volcanoes from the New Zealand and going through the Philippines, Japan, Aleutian, North America, South America. And this is what we call the Ring of Fire because the whole Pacific Ocean is surrounded by volcanic ranges. And this is due to the subduction of the different plates of the Pacific seafloor. And they're subducting below South America, the Nazca Plate, below North America, below the Aleutian, below Japan, Kamchatka, Philippines, etc. And because we have these subduction zones there, then it produces a long range of volcanoes. Another example, which is not in the Pacific Ring of Fire, is Indonesia. This is also a subduction zone, and this is basically the country with the highest density of volcanoes. So yes, there are patterns, but there are patterns in subduction zones, but also in rifts. So for example, in East Africa, middle of the Atlantic Ocean and Pacific Ocean, you also have a pattern, but the source of the volcanoes are different, and also the activity of the volcanoes are completely different.
One in the back.
Yeah, I don't know if there was a relation there, but do you think that further oil extraction might induce more eruptions?
Well, I don't think so. I don't think so because, you know, I mean, what happens, because I mean, when the volcanoes or magma bodies are producing hydrocarbons, they are old systems. They are frozen. All is frozen. It corresponds to old volcanoes. So we see the result now, but it will not reactivate volcanism there because the volcanic system is dead. So, and if we, I mean, that's actually a very interesting question in general to try to understand the interaction between surface processes and deep processes. For example, back to Iceland, I mean, there are some theories and some evidence that show that before, Iceland was covered with an ice cap, which was producing huge pressure. But then suddenly, 20,000 years ago, the ice cap melted. And so all this pressure was gone. And then this pressure decreased, was also transferred at depth, and it's possible actually it enhanced the melting of the mantle, and so triggered a lot of eruption. But I mean here, we talk about huge pressure differences. When you produce hydrocarbons from a reservoir, the pressure difference is very minimal. So I suspect that this effect is very negligible for what happens in the mantle. I mean, I suspect, of course, it's not a proof, but I think it's really, really small.
One thing I saw when I was there in Neuquén with you was that sometimes the volcanism can actually convert organic material to a sort of a viscous asphalt-like substance. So the magma itself is no longer a magma, it's actually some sort of an asphalt that moves almost like if it was a rock melt. Is that true?
No, it's more complicated than that. So what happens is that the magma, very, very hot, intrudes into these formations which contains a lot of organic matter. And then the magma cools down, etc. But it really heats up the organic matter into the surrounding rock. And then it cracks the organic matter. And this cracking can be so fast that it produces a lot of asphalt hydrocarbons within the source rock, producing like huge fluid pressures and almost, that's not almost, it's actually, we saw that in the field, it can produce big channels only made of and filled with the petroleum. And now what we see in the field, we see big veins of pure solid petroleum, and sometimes they can be 8 meters thick. It's huge. So it's almost like, it looks like a magma intruding, but actually it's the petroleum that was maturated by the magma. It was so fast that the pressures became so huge that it almost made like a volcano of oil. Mm. But yeah, we never I don't think we saw an active one. That might be impressive because when you see the thickness of the veins, it's like, wow, it must have been really strong.
One in the front. How much time do we have?
Maybe we should call this the last one.
The last question, okay.
Okay, thank you. So I know there's some mineralization processes occurring with the emplacement of the seals, and I wonder if you have you studied this this type of interaction between?
So my answer is no, because I'm very bad in mineralogy. I would love to, but I'm really, really bad. And but clearly, I mean, there are different things. So the fluids, I mean, the magma contains fluids, and they can trigger the deposition of minerals, different kind of stuff. But also the surrounding rocks can be activated thermally, and also the elements contained into these rocks can also be remobilized and concentrated around the intrusions. That's basically what I know. So that's not much. I cannot, but I mean, there are people actually working on that substantially. I don't.
All right. So that was the last question, and I would like to thank you again for your excellent presentation.
Thank you. Thank you.
Men det kommer nästan.